All right, so I thought on number one, I would show you guys a little bit of a different way than yesterday. This is kind of that alternative way, and I think the way these numbers worked out, I think this way that I'm going to show you is actually a little bit better than the way we did it yesterday. What I'm thinking is I'd like to get rid of that 5 before I did anything else. So what I'm going to do is divide both sides by 5. And why I think that is nice is because 10 divided by 5, it's a whole number, right? It's 2, not another fraction. So if I did do that, I'd end up with negative 1 plus 2/3 x equals 2. So for those of you that distributed, our steps are going to look a little bit different, and that's okay. I'll see if we end up in the same spot. Did you guys then, or would you guys at this point, would you guys agree with me that we would add 1 to both sides? So I'd go plus 1, that gives me 2/3 x equals 3. And then how would I get rid of that 2/3 times?
By 3.
You could multiply by 3, or you could get rid of the whole thing by multiplying by the reciprocal. That's right. So instead of multiplying by 3, I'm going to multiply by 3/2. That'll get rid of everything. So I'll go times 3/2 over here on the left, times 3/2 over here on the right. The 3's cancel, the 2's cancel, so the x is by itself. And what is 3 times 3/2? 9 over 2. Did you guys get 9 over 2 or maybe 4.5?
I got 4.
Same thing, right? So if you divided by 5 at the start, or maybe you distributed the 5 at the start, we should end up at the same spot, right? And so that's what I got. Other questions, comments, concerns? Okay. Number 2 then, write the slope-intercept equation of the line, passing through -4, 6, and 6, -4. What are the 2 things you got to have to write the equation or graph of a line?
Slope and a point.
Slope and a point. So my slope, I don't really know yet. My point, I've got 2 to choose from. Which one do I have to pick?
Either one.
It really doesn't matter. So, Josh, what do you say? First or second?
For the point?
Yep.
Oh, choose the second.
Okay, so 6, -4. So then my slope, I'm going to have to use that little slope formula. Slope, is slope change in x over change in y, or change in y over change in x? Which one is it? You know, of course, you can remember that the y is closer to the sky. Y points to the sky. I mean, there's whatever. It rhymes, so maybe it's good. So slope equals change in y over the change in x. And so for this one, I'd say my y2 is -4 minus y1, which is 6, over 6 minus -4. So essentially what you get here is -10 over +10, which of course is -1. All right, so then I'm going to use my point and that slope. I'll start it down here. It's going to be y minus -4 equals -1 times x minus 6. That is not slope-intercept form. That is point-slope form. I've got to do a little bit of work to get there. What would be a good first step to start getting to slope-intercept form? We always do a distributive property, right? So that would be a good first step. That would give me y plus 4 equals -1x plus 6. And then I would just subtract the 4 over. And when I subtract the 4 over, I finish with y equals -1x plus 2. Is that what you got also? Y equals -1x plus 2? Do you have any questions? It's good practice for our concept quiz today, for sure. Okay.
Would you, if we said -1x, or just
Totally, yeah.
negative x? Like
If you
does it
put
matter?
-1x or -x,
Alright.
has the same meaning, so yeah, good either way. Other questions? All right then. So the domain for this one here would be -3, 5, and 2. Obviously, there's a repeat of -3. You only have to list it twice. The domain would be 6, 7, 5, and 1. And then number 4, is number 3 a function, yes or no? What do you guys think? Just shout it out, yes or no?
No.
Okay, so I agree with the no. Number 3 does not represent a function. Anybody have an explanation as to why that would be, Ava?
There's more than one output, which is 5 and 6 for the same input, which is -3.
Yeah, so yeah, the input -3 has, how many outputs did you say?
2.
Yeah, it has 2 outputs, and those 2 outputs you said were 6, yeah, 5 and 6. Good explanation. Sir?
So, if you have different inputs, but they all have the same output, does that still follow a function?
It is, yeah, it is. So the definition of function is that each input has exactly one output. It doesn't specify whether the outputs have to be different or the same. The principle you mentioned actually will become a little more important later, maybe in Algebra 2 when you're looking at something called inverse functions. What you're talking about will matter there. For us to have a function, doesn't matter if all the outputs are the same. So maybe to illustrate what Joe's talking about, like if you had a different relation, and let's say the relation was like negative 1 comma 4, 0 comma 4, 3 comma 4, 9 comma 4, 12 comma 4, and 17 comma 4. Do you see how every single input has the exact same output? But do you also see how every single input has exactly one output? Just so happens that the output is the same for all of them. It's still a function. Later on, you'll find out that this doesn't have an inverse. That's not for us to talk about right now. So that's what we were talking about, right, Joe?
Yeah.
Okay. Any follow-up questions on any of that stuff? Okay, that is fantastic. I'm excited to do what we're going to do today. This will be kind of new. If you guys would flip over in your notes to our next page. This is good. This will be really, really good. Okay.
I love this stuff.
I'm glad to hear you're excited. I am too. So I want to show you guys a couple things here. I think hopefully we'll get through all of our examples. If we don't, that's okay. We'll continue. We'll spend like the next 3-4 days working on stuff like this. Okay? So yesterday we looked at systems of equations, but we looked specifically at the graphs of systems, right? So let me ask you about that. With the graph of a system of equations, the solution would be where the two lines do what?
Intersect.
So they intersect. That's where the lines cross, right? So if you had parallel lines which never intersect, what was your solution to the system? No solution, right? Because if the lines never intersect, there is no solution. But if they do intersect, there is a solution. So we're going to look at two other methods that you could use besides the graphing we did yesterday. We're going to look at two other methods in our class about how you could work with and solve a system. And this is going to be the second one. We'll do the third one tomorrow and through the rest of the week. So this method is called substitution. And if you think about what you understand about the word substitution, it's exactly what you think it is. Isn't the concept of substitution simply you're going to remove something from its place and put something equivalent where that thing used to be, right? So I think there's a lot of analogies to be used here. I think there's some important things. So try not to be distracted by the analogies, but I think this maybe will help a little bit. If you went to a restaurant and you were going to order some food, so especially a sit-down restaurant, it usually comes with sides, right? And let's say you sat down and you're looking at the menu and you're like, I would like to have, sorry? A cheeseburger, excellent. And then you look at this and it says, okay, the cheeseburger comes with a small salad. So like that's the standard, listen now, that's the standard side at this restaurant is you get a cheeseburger and they give you like this little salad in a little bowl, right? Would it not be reasonable for you to talk to the server and say, hey, I'd like to get this cheeseburger, but I would like to substitute the salad out and in its place get fries? Is that reasonable? Could that happen? Has that happened a million times? Yes. Or you could say, I'd like the cheeseburger, and I would like to substitute out the salad, and I'd like to replace it with some brown... No, not that. Listen, get the analogy. I'd like to substitute out the salad, and I'd like to replace it with a bowl of fruit. Like that would be reasonable, wouldn't it? Wouldn't it be unreasonable for you to say, I'd like to get the cheeseburger, please, and I'd like to substitute out the little salad and replace it with 19 large pizzas?
No.
Now, if you're a young man, you might be like, yeah, that actually sounds okay. Maybe we should do that, right? You get a little older, you realize that's not that great. Regardless, isn't that a totally unfair substitution? Because the value of that little salad in a bowl is a lot less than 19 large pizzas, right? That's not a fair substitution. Think about this. There's a good sports analogy, right? Don't substitutions happen a lot in sports?
Yeah.
So what if we're playing basketball and we've got our team I've got my team of 5 right here at this table. This is my team right here. The rest of you guys, my bench. Okay, now listen. So here's my team right here. These guys, let's pretend they're out there on the basketball court playing, and we've been going for a little while. And let's say, you know, we've been playing for a little bit, and Joe has gotten into foul trouble. He's a little tired or something. Got into foul trouble, and so the next dead ball, I'm the coach. I recognize, maybe Joe said, man, coach, I'm a little tired. I'm like, all right, the next dead ball, I'm like, all right, I'm going to substitute. Okay, so I'm like, all right, Joe, why don't you come out of the game? So now, Joe is out of the game, isn't he? Isn't there a blank spot on our court? Joe used to be out there. Now he's out of the game. I need to substitute somebody in there to take his spot, right? So say I decide, all right, well, I'm going to go ahead and substitute somebody. Who wants to substitute? Okay, we're going to go with Kyrie. Kyrie's ready to go. She's on the bench. She's been waiting to play. And I say, all right, now listen, hey, guys, hey, here's the analogy. I get Joe out of the game because he's tired. I'm going to substitute Kyrie in for him, right? So if Kyrie goes out there and she plays basketball, she makes a couple of baskets, gets a steal and a rebound, that'd be great, wouldn't it? But, and wouldn't that be great because isn't she doing the same kind of thing that Joe was doing earlier? She's playing basketball. She's trying to score some points, get a rebound, get a defensive stop, blah, 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 right? But what if I put Kyrie into the game for Joe, take Joe out, substitute Kyrie in, ref puts the ball in play, the other team throws it in, it's the other team's ball, and the first thing Kyrie does is she tackles the person with the ball. And not only does she tackle the person with the ball, she like does this awesome wrestling move and like pins them. Right? And she gets up, she's like, yeah, that was awesome. Woo! And she's like paying no attention. Everybody's like, what are you doing? Right? That as entertaining, like as wildly entertaining as that would be, like that's not what we want her to do, right? Because hasn't she gone into the basketball game and done something not equivalent to what Joe is doing? She's gone in there, there's a point to this. She's gone in there and she's done something incompatible with what Joe was doing. Therefore, kind of like the whole salad for the 19 pizzas thing, it was not a good substitution, was it? She might be a good wrestler and all that stuff, or a good tackler of people with the ball. I'm just making this up, right? But she doesn't understand basketball, right? And it's not a good substitution, right? It only would be a good substitution if we went there and she actually played basketball. That'd be good. So guys, here is the big point. A substitution is only valid, it's only good if the thing that you took out and the thing that you put in have the exact same value. Make sense? It's only good if you substitute something in that has the same value for the thing you took out. It's true in math as well. So take a look here at our first example. I've got this system of equations, and it says I want you to solve this using the substitution method. So substitution simply means you're going to take an x out of one of the equations, or you're going to take a y out of one of the equations, and you're going to replace it with something equivalent. And this is where we get into something that I think sometimes is really challenging for people, because we've always seen this symbol in a wrong light. This symbol right here, and this symbol right here. It does not mean, and my next step is. It doesn't mean, here's my next thought. It doesn't mean, here is a step. What it means, this is fundamentally huge, it means that the stuff on the left side of that symbol and the stuff on the right side of that symbol, regardless of how they look, they might look the same, they might look different, regardless of how they look, they have the exact same value. Does that make sense? Final analogy. Help you understand this equal sign. What if you had a $1 bill and I had 94 pennies? Now, if you're a little kid, you wouldn't get this. My little daughter is still at this place. She doesn't understand this. She would gladly trade a $1 bill for 94 pennies. Because to a little kid's mind, doesn't 94 pennies look like it's a whole lot cooler than a piece of paper? Right? It's a handful of copper coins, right? I mean, that looks awesome. This green, dirty piece of paper? I mean, come on. No way. She's thinking she's getting the deal of a lifetime, whereas she's getting shorted, right? But if I had 100 pennies, a handful of pennies, and you had a $1 bill, don't they have the exact same value? Guys, they look nothing alike. It's ridiculous. I mean, it's a handful of metal versus a piece of paper. How could those possibly have the same value? Well, the U.S. government has told you that this handful of pennies is worth $1 and this paper is worth $1. So it would be fair for us to trade those, wouldn't it? Wouldn't be fair for the person with a pocket full of pennies anymore, right? Because You got a pocket full of pennies. It's better to have the dollar. But the value is the same, right? So when I look up here and I say, hey, I got all these equal signs, what does that mean? Well, that tells me that y has the exact same value as this. And so if I wanted to, I could replace any other y's that I see with 5x minus 2. Does that make sense? And they don't look anything alike. There's a y and there's a 5x minus 2. They don't look anything alike. But because of that equal sign, that's like the U.S. government saying 100 pennies and a piece of paper with a 1 on it, they have the same value. So what I could do, here's what I would need to do here if I was going to substitute. I'm going to take this second equation, the 6x plus y equals 9. What I'm going to do is I'm going to remove the y from the game. Or I'm going to get rid of the salad from my order, right? I'm going to remove the y from the game, and I'm going to replace the y with the only thing that I can replace the y with, and that would be? Because they're equal. That's right. So in place of that y, I'm going to put 5x minus 2. The reason why we're doing this is we want to take these equations and take them from an equation with 2 variables down to an equation with 1 variable, because we can solve that. Okay? You see what I've done here? I hope you can see this. I've replaced the y with the only thing that the y is equal to. I've replaced it with 5x minus 2. Now once I've done that, I've got a little bit of simplifying and solving to be done. So let's do that. What kind of simplifying do you see there? 6x plus 5x minus 2. Say again, Callie?
Combining the 5x and the 6x.
That's right. And if I did that, what would I get?
11x.
Yep. 11x. Those are like terms. So 11x minus 2 equals 9. And now that I've simplified them down to a relatively straightforward equation to solve, would you guys try to get rid of that 11 first or the minus 2 first?
Minus 2.
All right, so we add 2 to both sides. So when I add 2 to both sides, I get 11x equals 11. And then to get rid of the 11, divide by 11. So dividing by 11, I end up with x is equal to 1. Okay, so this is one of those moments where you feel like, hey, yeah, I got it. Solved this. I'm done. But remember, let's go back to what we did yesterday. The solution to a system of equations is where the 2 lines intersect. And I've tried to make a point of emphasis on this. I think you guys are getting it. You can never say that a point is 1. Don't you have to have an x comma a y? X and a y coordinate? So if x equals 1, that's only half the answer. Do you guys have any ideas on what I could do to find the y that goes with that particular x? What do you think? Into which equation?
Y equals 5x.
It shouldn't matter, but it shouldn't matter, you're right. But there's an easier one, right? Which one would be easier? Because the y is already by itself, right? So that would be an easier way to go. You could do the other one as well. But I would just take this, and I'd say, all right, well, I know that x is 1, so then y must be 5, parentheses 1, minus 2. I've replaced the x with a 1. Follow the order of operations. Don't we get 3?
Yep.
So my answer, my solution to my system is 1, comma 3. And I would ask that you try to write it in that form, 1, comma 3. Okay. I can tell that some of you have at least seen this before. I can tell some of you are like, I don't know, I might have seen this, but I'm unsure, and others maybe haven't seen it. All those are okay. Do you have any questions right now? Okay, let's at least do one more example here. So let's do oops, that's not what I wanted to do. That's what I wanted to do. Let's do number 2. Okay, so if you guys would look at number 2 with me. Same exact, oh, it's lagging, isn't it? Look at number 2. You can see it, I can see it, but the screen is lagging. If you don't have your notes, then just peek with somebody else. Oh, there it is. Example number 2 says, solve the system using substitution. So it's the exact same instructions. But if you look carefully at the setup, if you compare it to what we had in number 1, it is slightly different. Can anybody point out an important difference between 1 and 2? What do you think, Josh?
There's no y equals.
Yeah, the y in no place is the y by itself. Did you notice that, number 1? That made our setting up our substitution pretty straightforward. Here, we don't really have that. But could we get that?
Yeah.
Yes.
And I think we want to do that, right? Any suggestions on what I could do to get to that place? Noelle?
So I would say we should use the bottom to the y. So
No number connected to the y.
yeah.
Yep.
And then we just can subtract 2x to the
Yep.
other side, like kind of like looking at it in form, but then that gets the y by itself.
So y equals 3 minus 2x. I agree. So I'm going to use that relationship to help me with my substitution. What do I want to do? What do I want to do? Let's let me let you guys try this. Okay. Why don't you guys take just a couple of minutes? It's maybe a little earlier. I'm feeling confident, like watching you guys. I feel like a lot of you are starting to get this, or maybe you're remembering it. Take a few minutes and give it a shot. Look at your answers here in a minute. This will be our last one for the day. Okay, so if y equals 3 minus 2x, what that means is that anywhere else I see a y, I can get the y out of there, and I can put a 3 minus 2x in place of it. So I'm going to write 3x plus 4 blank equals negative 8. So that other equation, what I've done is I have removed the y. There it was, and now you can see it's gone. Remove the y out of that equation, and I'm going to be replacing it with the only thing that y is equal to. Y is equal to that. So I can replace the y with 3 minus 2x. So that gives me this right here. Did you all see that this was a little bit different than the first one in that you had to use a distributive property? A little bit unique compared to the other one. I would say that distributive property is very common with substitution. So the 4 gets distributed, so it would be 3x plus 12 minus 8x equals negative 8. Did you guys do a little cleanup work there with the adding of like terms? You definitely want to do that first. So these two terms right here are like terms. That would be negative 5x plus 12 equals negative 8. And now we're down into kind of our standard equation solving process. I would subtract 12 from both sides, giving me negative 5x equals negative 20. And then I'd divide by negative 5. That would give me x is equal to 4. Of course, you guys know that's only half the answer. It's a point, so it's got to be x comma y. Did you guys plug back in?
Yep.
And isn't this the easier of the two equations to use?
Yep.
So I would write y equals 3 minus 2 times 4. Following order of operations, I get 3 minus 8, which is negative 5. So 4 comma negative 5 is my solution to my system. And I'm done. Questions? Yes, ma'am.
I'm still just confused on the last part on how to get the second point.
So you're okay with the whole x equals 4?
Yeah.
Okay. So then you know then that the answer has to be a point. So it really does have to be x comma y. That makes sense? So you have a lot of freedom. I think sometimes people get confused and think that they have no freedom. Here's the truth. I'm going to highlight these in purple. You have lots of options. You have this as an option. You have this as an option. You have that as an option. All of those relate x with y. And anytime you have a relationship between x and y, if you know x, you can find y. Or if you know y, you could find x, right?
Okay.
And so the honest truth is you could use any of those three. In other words, you could say x equals 4, and you could plug it in to the top one, the middle one, or the bottom one. And if you do everything right, you should get the same output for all of those. Okay? So what I would say is that this one would be the easiest to do that with because the y is already by itself. If you did option number 1 or option number 2, you could totally plug a 4 in for x. It's not a big deal. But then you'd have to do some extra algebra steps to get to the output. Whereas if you chose the option number 3, it's already y equals. So all you got to do is plug the 4 in for x, do a little arithmetic, and you're done.
Okay.
Does that make sense?
Yep.
So you have lots of freedom. No one's telling you that you have to do this one. You have other choices.
Okay.
I would just have a suggestion to use the one I said. Anyone else? Okay, this, in my mind, this is an encouraging start. I feel like you guys are doing okay. We'll continue to do a little bit of substitution tomorrow. We'll get into elimination, which is our final method tomorrow as well. Just do a lot of practicing. So if you guys would, get all your desks facing the front. Grab a divider right there behind Victoria if you are going to be sitting by somebody.
Mr. Anderson, are you available during business lunch today? Do you see
You know,